This is a brief introduction of how to solve systems of equations using inverse matrices. The first thing you need to know about using inverse matrices is what an identity matrix is. It seems kind of odd, but you do need to know that. So an identity matrix for a 2 by 2, which means 2 rows by 2 columns, looks like this. For a 3 by 3, which is 3 rows and 3 columns, looks like this. And for a 4 by 4, which is 4 rows and 4 columns, looks like this. What you may notice about each of these identity matrices is that the diagonals are 1s starting in row 1 and column 1. There's a diagonal of 1s, and every other component of the matrix is 0. Notice that all identity matrices have to be square, which means the number of rows is equal to the number of columns, and that the diagonals are 1 with every other component of 0. This is kind of like a 1 if you were multiplying something. So if there's a matrix A and it's multiplied by its inverse, A to the negative 1, then the product is the identity matrix. So if you take a matrix, multiply by its inverse, you will get the identity matrix, or this matrix up here. This is kind of like in regular multiplication, where 3/2 is the inverse of 2/3. So if I take 2/3, kind of like a matrix A, I multiply it by its inverse, like the inverse A, and I get 1, which is like the identity matrix. It's very similar. It's just in the matrices world. So one way you may be asked if two matrices are inverses of each other. So a way to check that is if the matrices multiply together to form the identity, then they must be inverses. So if I have a matrix and I multiply it by what I think is the inverse, I will get the identity. If this is true, then they're inverses. So we have an example here where we've taken a matrix and another matrix, and we want to know, are they inverses? Well, one way to do it is to just simply multiply them by each other and find out if you get the identity. So let's look at how we did this. When you multiply matrices, you take the row of the first one and multiply it by the column. So 4 times 4, and then add it to 5 times negative 3. You take the same row and multiply it by the second column. 4 times negative 5 plus 5 times 4. Now you're going to take this row and multiply it by the first column. So 3 times 4 plus 4 times negative 3, and that's in this position. And then you take this row and multiply it by the last column, 3 times negative 5 and 4 times 4. Now you simply do the addition and subtraction and simplify. So I get this to be 16, negative 15, negative 20, positive 20, 12 and negative 12, negative 15 and 16. When I simplify this, I get this matrix. I multiplied him times him, and I got this. This is the identity matrix, so therefore the two matrices that I multiplied must be inverses of each other. Okay, let's do another one. Okay, we're going to take this matrix and determine, are they inverses? Well, we're going to multiply this row times this row times this column, the bottom row times the column, and the bottom row times the last column. And I put them in their respective order. When I simplify this, I get these values. And then I evaluate these values and determine that I do not get the identity matrix. If I don't get the identity matrix, it means that these two original matrices were not inverses. Okay, so let's talk about how to get inverse matrices and what we use them for. Basically, we use inverse matrices to solve equations, okay? Keep in mind that you can add matrices together, you can subtract matrices from each other, you can multiply matrices by each other and by a scalar factor, but you can never divide by a matrix. Well, that seems kind of odd. Then how do you rearrange equations if you can't divide by a matrix? So, to solve a matrix equation, instead of dividing, you have to multiply by the inverse. Well, that sounds a lot like dividing, but it is different. So if you had a matrix A, okay, and you had this equation where you had matrix A times a variable matrix equals a constant matrix, how do you isolate x and y? If I can't divide by this matrix, how do I get rid of it so that I can put it on the other side and solve for x and y? Well, this is how. You take the matrix, you multiply it by its inverse. If I multiply this side by the inverse, I also have to multiply the other side by the inverse matrix. When I do that, these two cancel out. Well, you might think to yourself, well, we just said that if I multiply a matrix times its inverse, I get the identity matrix. But if I take the identity and multiply it by anything, I end up with the same matrix anyway. So basically, this is like these two cancel out. Because if you multiply this times that, you're going to get the same number, the same matrix. So if I multiply this times the inverse, I have to multiply the other side times the inverse. Well, now I'm left with x and y, my variables isolated, and I simply have to multiply the inverse times the other side. So again, instead of dividing by a matrix on this side, to get rid of this, I simply multiply both sides by the inverse. This is kind of like if you had this equation. If I had 2/3 x is equal to 10, and I want to isolate x, I can either divide by 2/3 or multiply by its inverse, 3/2. If I multiply this side by 3/2, I have to multiply that side by 3/2, but that's okay. This side cancels, and I get the answer to my solution. We're doing a similar thing up here. Not dividing, but multiplying by the inverse. So how do I calculate the inverse matrix? Well, here is the formula. If I have a matrix A, it's a 2x2 matrix, where I have numbers in the position A, B, C, and D, then the inverse matrix is defined as 1 over the determinant of A times this matrix. Well, first let's look at the determinant. The determinant of A is simply AD minus BC. The determinant of A is AD minus BC. That's what the determinant is. As long as that's not 0, then the inverse is defined, because you can't divide by 0. Now let's look at this other part. You get this fraction, and then you get this funny matrix, because this is multiplied by this. Look at A and D. A and D switched places. I took my original matrix, and I switched places. Look at B and C. B and C switched signs. So I took my original matrix and switched signs. So let's do an example. So if I have a matrix A, the inverse of that matrix is 1 over the determinant times this. So let's solve this equation by using the inverse matrix. I need to isolate x and y. So that means I've got to get rid of this matrix. I can't divide by the matrix, but I can multiply by its inverse. What I will get is x, y, the matrices, the variable matrix, is equal to the inverse of this matrix times the constant matrix, because I simply multiplied both sides by the inverse. So here's my xy. Now here's the inverse. Remember the formula, 1 over the determinant. The determinant is 3 times 5 minus negative 7 times 1. That's the determinant. Now I have that new matrix. Remember 3 and 5 switch places, and negative 7 and 1 switch signs. This came from the formula right here. Okay, so now I just simply need to work out each problem. 3 times 5 is 15. 15 plus 7 is 22. Okay, this stayed the same, this stayed the same. Now this is scalar multiplication, so I need to multiply this 1 over 22 times each of these. So 1 over 22 times 5, 1 over 22 times 7, and so forth. Each item was multiplied by this. So now I need to multiply this matrix times this matrix. Well, remember, you're going to multiply the row times the column. So 5 times 12 is 60. 7 times negative 8 is negative 56. I'm going to multiply this row times this column. Negative 1 times 12, and 3 times negative 8. Now I simply simplify. 60 minus 56 is 4. Negative 12 and negative 24 is negative 36. Now that I have these fractions, I can divide them by 2, so I get these answers. So if you look at the final matrix, x is equal to 1/11, and y is equal to negative 18/11, and that is my answer. Okay, let's look at another problem. What you may be given is an equation, and you have to go from the equation to the matrices. So the first matrix you need to do is called the coefficient matrix. You take the coefficients, make sure your variables line up, by the way. So make sure your x's are together, your y's are together, your constants are on the other side of the equal sign. Or if you have r's and s's or v's and u's, they need to be lined up. So my x variables are 2 and 5, and my y variables are 1 and negative 3. My variables are x and y, and my constants are 8 and negative 12. If you look, basically what I did was I just took the 2 and the 1 and the 5 and the negative 3, and I simply just pulled them from the formula there, the equations. Okay, so what did we say before? I can't divide by this matrix because in order to solve for x and y, but I can multiply by its inverse. If I multiply this side by the inverse, it cancels. If I multiply this side by the inverse, that's what I'm going to do over here. So it's 1 over the determinant. The determinant is 2 times negative 3 plus 1 times 5. Remember the determinant, that's the determinant. Remember my A and my D switch places, and my C and my B switch signs. Okay, so then my denominator becomes negative 6 and 5. So this is supposed to be a minus. There you go. Okay. Negative 6 and negative 5 become negative 11. This stays the same. Okay. Now I distribute. So negative 1/11 times this number is 3/11, 1/11, 5/11, and negative 2/11. Okay. Now I'm going to take this row and multiply it by this column and add them together. Okay. So I get 24/11 minus 12/11 and 40/11 plus 24/11. Okay. When I simplify that, I get 12/11 and 64/11. And that is my answer. So x is equal to 12/11 and y is equal to 64/11. And that is my answer. Good luck.